what would you need to know? What would be something?
Velocity that we went from 10 to 7.
Yeah, how fast does this boat go?
How long?
Yeah, if I just told you, the boat velocity varied, but the whole thing took 2 hours. That would be an answer. That would be enough to do it. Or I could do what I am going to do is I'm going to tell you the boat's going 10 miles an hour. Okay, it's going 10 miles an hour relative to its current. So this took an hour to get from here to here, another 0.7 hours to get from there to there. So 10 miles an hour, we went 17 miles. Took us 1.7 hours. So for this particular problem, I'm saying boat goes 10 mph, which means t equals 1.7. Right? And so now we came to that step up. Okay? So I'm going to put this guy, multiply this into my 5. So I can say that P current equals 1.7 times 5. Let's do it right here. 8.5. Is this my unit still miles per hour? By multiplying by T? No. It's miles per hour times hours. So the per hour goes away, so it becomes miles. So I have 8.5 miles, so now I am going to be the same units as the rest of my stuff here. It's still times the cosine of 45 pi plus sine of 45 j. And so I would tack that on. I would tack that on to this right here. 0.8, well, I'm not actually going to do this to show what this point. So cosine 45, roughly 0.707, multiply that by 8.5, tack that onto this. Again, 8.5 times 0.707, cosine 45, tack that onto that. And that would be our final position of probably up there someplace. Okay? Does that make sense? Well, it depends on how we're defining our 10 miles. I mean, yes, it could. If this was like a fixed in space 10 miles, this is some, piece of rock that's fixed to the seabed, and this is another piece of rock fixed to the seabed, then yes, then we're not really traveling 10 miles. I'm saying the boat, relative to the water around it, is going 10 miles.
Okay, just so I fully understand, so we're going to take we're just taking the P current and then we're adding it then to the resultant.
Yeah.
Okay.
So I'm saying this guy right here is R plus P current. Gets us up to this. Up there. Okay? Does everybody go with this? Okay. So, a similar thing to do with velocities. Another problem. So say we've got a pickup truck heading north, 20 miles an hour. Some enterprising, no doubt completely sober soul is standing in the back of said pickup truck and throws a football due west, 45-degree angle up. They're going to the Hail Mary, trying to get some distance on this guy at 50 feet per second. And we want to know what velocity that football as it leaves this eminently sober person's hand.
Where are you going?
I don't mean to describe you every Friday night, but so I have a northbound pickup now doing velocities. That's sort of my point here. We did a position problem, now we're gonna do a velocity problem. I know, I'm hoping this is all review. You've had physics, we have post growing class. I just wanna make sure everybody can do these sort of fun basic problems before we do the more complex stuff. That's sort of my purpose with this. Okay, and then we're gonna throw a football. It doesn't really matter, 'cause we're gonna be ignoring drag, so it doesn't really matter what the shape of the thing is. Throw a football due west up at a 45-degree angle at 50 feet per second. Okay. So these are each vectors. Sadly, I've done this in three dimensions, so I have to, okay. So, you can see here, I would like to still have this be north. So we've got this guy going north at 20 mph. And then we're going to puck the football due west, I said, so that's that way. That's going that way. This is at 50 feet per second, except this is up at 45-degree angle. This is where I'm not actually going to attempt to draw that. I could try and break out some isometric, but I don't think it goes super well. So does everybody understand this thing's actually coming up like this? Okay? Does that make sense? We're looking down, we're in a helicopter looking down at this lovely scene, and we see the pickup truck going that way, and we see the football coming off, and it's coming off in this direction. It's coming up at a 45-degree angle. Alright? So can I add these guys? They're both velocities. Can I add them up?
You can burn to the same.
Unit.
Yes. With a little bit of conversion, I can. So I'm gonna work with feet per second. So I'm gonna convert my 20 miles per hour. So I'm gonna say my 20 miles per hour, and I'm gonna multiply this by 5,280, which is a good number to know, feet per mile. Now my miles will cancel out. And then I'm going to multiply that by 1 hour per 3,600 seconds, which is 60 squared. So then my hours will cancel out, leaving me with feet per second, what I wanted. So I have 29.3 feet per second. So now I've got the same units. Now I can add this stuff up. So I'm going to do that. So how do I write this one? I want to do the same way I do my position stuff. So now we're talking velocities. How do I write this in terms of IJK unit vectors? It's 29.3 feet per second heading north. So this is V pickup. Okay. So it's going to be, I'm going to start with I. How much I do I got? 0. I got 0 I. There's no I involved. This time I'm going to pull my 29.3 out.
Do you have to start with I, or can you just not use it again?
No, you got to have it in there. You got to have 92 in there at some point. Okay, but yeah, still got 0 I. We're not going, I is that way. We're not going that way with pickup. We don't have any of that. What about J? How much J do I have? Huh? How much J is north?
90 degrees.
I mean, so should I write some function for J? Should I write a number for J? Well, how much J do I have in this vector? It's this vector right here. 29.38, since I pulled that outside the parentheses, so it's just one. So I have just J. One J. Does that make sense to everybody? Okay, and then the last would be K, we're working in three dimensions on this one. How much K do I have? K would be up down, K is coming out of the board, that's K.
9.8.
That's acceleration, truck's not accelerating up and down, it's driving on the road. So, more likely bounce through a field, but anyway. So, we don't got any of it, so 0 K. So that's the velocity of the pickup. Then we want to know the velocity of the ball. Assuming there was no pickup, we're going to end up adding them. It's just the ball, it's just in and of itself. So ball from rest. Or not on pickup. Again, I'm going to pull my 50 feet per second out. That's just saving me having to keep writing the thing. So I have my 50 feet per second. So now, how much I do I have?
-1.
So this guy, we have 50 feet per second coming out of the board like this at a 45-degree angle. Positive eyes that way, negative eyes this way.
Zero.
Yes.
Negative sign 45.
Okay. So this is coming out of the board like this. This distance from, I'll do dimensions. So this is coming out 50, like this. I want to know, I'm coming out, I told my tape measure at 50, so to speak, how far am I over this way? Right along the board. It's the cosine of that angle. Cosine of the 45. And it's negative because we're positive that way and we're headed this way. So, negative cosine of 45 degrees in the I direction. How much J do I have?
0.
J's north, basically where the pickup truck's going. I said we were throwing this ball due west. We don't have any J, so we're 0 J. And then what about K? K's coming out of the board. Yeah, do the sine of 45. And so this particular problem, wouldn't matter if I put sine or cosine, because sine of 45 equals cosine of 45. But if I had said, it probably would have been better if I had said we do this ball at 30 degrees, then the numbers feel different, but that's how I did it, so, oh well. Was that a question about why this is? Yeah. So sine of 45 degrees. Okay. Alright, so this, now we can just add these guys up, got the same units, they're both velocities, we can have no problem. So